Okay, we are recording. Let's start by going over what we discussed last time, and then we can go over any homework questions that you have. Okay, so last time we talked about generalized unions and intersections. Okay. So we talked about the union of more than two sets, or the intersection of more than two sets. Okay. And we also began our discussion on functions, right? We defined what a function is. We talked about the domain and codomain of a function, as well as the range of a function. We defined what an image and a preimage is. Okay. And we discussed different ways of writing down functions. We discussed picturing a function using a Venn diagram and also using the f of x notation. All right, and we also discussed combining functions by either adding them together or multiplying them. Okay. All right. Okay. So all that was last time. Any homework questions? Okay. So we have question 47 and question 51. All right, let's look at 47. 47 is that's from 2.1, is that correct? Yeah. That's from 2.2? Okay, so 47 from 2.2. All right. Yes. Okay. All right, so the question is as follows. Let AI be the set of integers from 1 to I. 1, 2, 3, dot, 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 all the way up to I. Okay. For I going from 1 and up. Okay. So you're asked to find the following. For part A, you're asked to find the union of A sub I going from 1 to n. Okay. And for part B, you're asked to find the intersection. Okay, so let's do the union first. All right, so the union of each of the sets, all right, is equal to what? All right, well, what's A1 going to be? A1 is the set whose only element is 1. Okay, A2 is 1 comma 2. A3 is 1, 2, 3, etc., etc. Okay, all the way up to A sub n, whose elements are with the number of integers 1 through n. Okay, so this is the union of all these sets. This is A1, the union with A2, union with A3, all the way up to A sub n. Okay, so if we're doing the union of all those sets, we're just combining them all into one big set. So everything goes into the set. So it's going to have all of the integers from 1 to n. So it's just A sub n. Okay, so that's part A. Part B will be the intersection. So the intersection from I equals 1 to n of A sub I. That's the intersection of all these sets, A2, dot, 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 all the way up to A sub n. Okay, so what's in this set? Only those elements that are in each and every one of the sets here. Okay, so which element is the only element that all the sets have in common, the number 1. So the intersection will just have that number. Okay, so it'll be a sub 1. Okay. All right, let's now move on to the next problem. Somebody asked about number 51. All right. All right, 51 has a couple of parts. Maybe we won't do all of them. Find the union of a sub I going from 1 to infinity, and the intersection of a sub I going from 1 to infinity, if for every positive integer I, all right, and part A says if for every positive integer I, a sub I is the set negative I plus 1, dot, 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 all the way up to negative 1, then 0, then 1, then dot, 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 then I plus 1. Excuse me. Then I minus 1, then I. Okay. So in other words, a sub I is the set of integers from negative I to I. Okay, so A1 is the set 1, 0, 1. A2 is the set 2, 1, 0, 1, 2. Okay, A sub 3 is the set 3, 2, negative 2, negative 1, 0, 1, 2. A sub 3 will be negative 3, negative 2, negative 1, 0, 1, 2. Okay. And that pattern continues. Okay. So the union of all these sets from I equals 1 to infinity of a sub I will be what? Well, it will have 0, negative 1, negative 2, etc., etc. And that will continue forever. And it will also have 1, 2, etc., etc., and that will continue out to the right forever. Okay. So what is this set? What is that set? Yep, that's the set of all integers. Okay. That's the set of all integers, so that's the set Z. All right. Each time, each set is adding new elements, right? A1 adds negative 1, 0, and 1. A2 will add negative 2 and 2. A3, negative 3 and 3. Oh, I'm missing the 3 there. Okay. All right. A4 will add the negative 4 and 4, and so on and so forth. This goes until infinity. So it keeps going out to the left and to the right forever. So that's the set of integers. Okay. What about the intersection of all these sets? The intersection from I equals 1 to infinity of a sub I. Okay. Well, which elements are the only elements that will appear in every set? The numbers negative 1, 0, and 1. Right, so a sub 1 will be the intersection. Okay. So somebody asked here in the comments, they asked, why are we counting for negatives if it says for every positive integer I? Okay, it's a good question. If I is a positive integer, right, what is this? How is the set defined though, right? It has a negative I here. So if I is 1, here's a negative 1, and here's a 1, right? If I is 2, this would be negative 2, and this would be negative 2. Okay, so in the definition of the set here, we see it has negative I. So if I is positive, negative I is there as well. Okay. All right, and the other, Yes, we discussed in the beginning of class there were some technical difficulties with Blackboard, so the quiz has been delayed till Monday. Okay. All right. All right. I see a few people are happy. Quite a few people are happy about that. All right. Okay. So that was part A. Does anyone want to see part B, or should we move on to the next question? Okay. Okay. B2. All right, let's do part B as well, and then we'll move on to the next question. All right. So for part B, this time each set A sub I is defined as the set that includes negative I and I. So for this one, A1 will be negative 1 comma 1. A2 will be negative 2 comma 2. Okay. A3 will be negative 3 comma 3. And so on and so forth forever and ever. So the union of A sub I going from 1 to infinity, will include what? It will include all of these numbers. So we'll have negative 1, negative 2, dot, dot, dot. There's no 0 here. 1, 2, dot, dot, dot. So this includes all of the integers except for 0, right? So one way I could express that would be to say that this is the set of all integers minus 0. Okay. It's the set of all integers except for 0. It's all non-zero integers. What about the intersection? Which elements are in all the sets? Are there any elements that are in that exist in every set, that are members of every set? Right? No, exactly. Right there, yeah. There are no elements that are in every single set, that are members of every set. So the intersection would just be the empty set. Okay. All right, so that would be part B. All right. All right, somebody asked for C and D as well. C and D deal with intervals. I'm not going to really ask you about intervals on a test. So I'm just I'll leave that for now. I don't want to spend too much time on it. All right. It's just saying that each set A sub I is equal to an interval. So it's all the real numbers between negative I and I. Okay, so it's similar idea, except instead of integers, it's real numbers. All right. The intervals. I want to ask you about intervals on a test. Right. So the 51 C and D, I wouldn't ask you that on a test. Okay. Yeah, it's the same idea. It's just it's real numbers instead of just integers. Okay. Let me move on to the next question now. Somebody asked for in 2.37a. Let me take a look at that. Okay, so in 2.37 part A, you were asked to find the domain and range of the following functions. Okay, so what is the domain and the range? In part A, you were told the function, you were given the function that assigns to each pair of positive integers the maximum of these two integers. Okay, so a pair of positive integers, right, would be a set of two integers, right? So it takes in two integers. So the domain would be the set of pairs of integers, and the range would be just a set of integers. Okay. All right. So the domain would consist of pairs of integers. Okay. and the range would just be the set of integers. Okay, so it's the maximum function. So the maximum of you plug in two integers. Oh, excuse me, positive integers. All right, pairs of positive integers. Positive integers, and the range is the set of positive integers. Okay, so you plug in two integers into the function, 2 and 3, let's say, and it gives you the larger of them, 3. Okay, so you're plugging in two integers and you're getting out one integer. All right. Okay. So let's see how your textbook put the answer here. Somebody made a comment here. Let's see. Give me one moment. Okay. Yeah, so yeah, exactly as Hania said, that basically the textbook puts it this way. The domain is the set of positive integers times the set of positive integers, right? That's a Cartesian product, right? So that's the pairs of positive integers, right? It's a comma b, it's the set of all a comma b where a and b are integers. And the range is just the set of positive integers. Okay. Any other questions? All right. So let's now continue with our discussion on functions. Okay. We're going to start today by discussing what a one-to-one function is and what an onto function is. Okay. These are terms you might have heard previously. All right. So let me remind you of the definition of a one-to-one function. All right. So a function f is said to be one-to-one okay, also called an injection. If and only if f of a equals f of b implies that a equals b. For all a and b in the domain of f. Okay. Now, a different way of expressing this would be to express it using the contrapositive. So I could also say this in the following way. F is one-to-one. Okay. If and only if f of a does not equal to f of b whenever a does not equal to b. Okay. And then I'll demonstrate what this means in a moment. Okay. All right. Also, one more note here. When I say one-to-one, I'll sometimes use the shorthand as follows. So this symbol here means one-to-one. Okay. Okay. Oh, we're still on 2.3. We're still on functions. Okay. All right, so let me demonstrate what it means for a function to be one-to-one. Let's start with a Venn diagram. Okay. So let's say this is my domain A, this is my codomain B. Let me do like this, one. Okay, let's say A has three elements, A1, A2, A3, B has two elements, B1 and B2. If B1 is assigned to two elements in A, all right, so let's say f of A1 equals B1 and f of A2 equals B1, okay? So f of A1 equals f of A2, okay? If this happens, if B1, if an element in my codomain is assigned to two different elements in my domain, so B1 has two or more distinct pre-images, then the function is not one-to-one. So this function is not one-to-one because B1 has more than one pre-image. Okay, so if I can plug in two different values from the domain into the function and get out the same value in the codomain, then the function is not one-to-one. Okay, it's only one-to-one if every assignment is unique. Okay, so let's say I have a function that looks like this. Okay, so f of a1 equals b1, f of a2 equals b2. Okay, here every assignment from elements in the set B in the codomain is unique, right? Every image has at most one pre-image, so this would be one-to-one. So this is one-to-one because every image has a unique pre-image. Yes, exactly, right? There are, in other words, there are no repeating y values. If a y value repeats, then it's not one-to-one. Okay. All right, let's see an example with some actual functions where the function is given as a rule. Let's say I have a function f of x equals x squared, okay, where f is a function from the set of real numbers to the set of real numbers. So my domain and codomain are the set of real numbers. Is this function one-to-one? Is f one-to-one? The answer is no, right? How do I check? Well, to show that the function is not one-to-one, to show that it's not one-to-one, I have to be able to find two different x values that give me the same y value, two different values, two different elements in the domain that give me the same element in the codomain, okay? So for this function, if I plug in -1, what do I get? I get -1 squared, which is 1. And if I plug in 1, I also get 1 squared, which is 1. So two different x values give me the same y value, right? -1 and 1 are both assigned 1 from the codomain. Okay, so f of -1 equals f of 1 equals 1. So I have an image, 1, which is an element in my codomain, that has two different pre-images, -1 and 1. Okay? So therefore, this thing is not one-to-one. No, it's not one-to-one. All right. Okay. Another way to see that would be to do the following. Okay, so one way to show that it's not one-to-one, this is probably the easiest way, would just be to find an example, find two different numbers that I can plug in and get the same number. Okay. Another way you can show it's not one-to-one is by, instead of finding two particular examples, sort of pick arbitrary numbers x1 and x2. So let's say x1 and x2 are both elements are elements in the domain. Okay, there's some random numbers. Okay, f of x1 would equal to x1 squared. F of x2 would equal to x2 squared. Okay. What I can do to show that this thing is not one-to-one is I could set those two things equal to each other, right? Set f of x1 equal to f of x2. All right. And now let's see if I can solve this thing. So meaning let's get rid of the squares. Okay. So if I get rid of the squares, I'm going to take the square root. If I take the square root of both sides, right? Anytime I take the square root of something squared, it's always positive or negative, right? So that means that x1 is plus or minus x2. Okay. So that again tells me that there's two different numbers that I can plug in, either the positive x2 or negative x2. Okay, and I'll get the same y value. Okay, so there are two different numbers you can plug in to get the same y value, right? Namely, positive x2 and negative x2. Okay. All right. Right. So in other words, if this shows us that if f of x1 equals to f of x2, x1 does not necessarily have to equal to x2. It could be negative x2. Okay. Right, and to be one-to-one, when f of x1 equals f of x2, x1 has to equal to x2. That's from the definition from before. Okay. All right. Let's try a different function now. Let's say I gave you well, let's try the same function, f of x equals x squared. But let's say my domain and codomain are different now. Let's say I change my domain to the set of natural numbers, and my codomain is the set of, let's say, the set of real numbers. Okay. Now is this function one-to-one? Okay, so I've restricted my domain to the set of natural numbers. Is this thing now one-to-one? Yes, it is, right? Why? Because I've gotten rid of all the negative numbers. I'm now no longer allowed to plug in negative numbers for x, right? So each x value will have a unique y value, okay? So yes, okay, it is one-to-one. Okay, we got rid of all the negative numbers. Numbers from the domain. So there won't be any repeating y values. Oh, what does the arrow mean? That was from last class. This tells us the domain and codomain. So this means f is a function that takes the natural numbers and assigns to them real numbers, right? So this tells me my domain and codomain. Okay. It's a notation to tell us that. Okay, let's try another function. Let's say I give you the function f of x equals x plus 1. Okay. And let's say f is a function from the set of real numbers to the set of real numbers. So the domain and the codomain is R. Okay. Is this function one-to-one? Okay. So here the answer is yes, it is, right? As somebody pointed out, it's what we would call a linear function. How do I check that it's one-to-one? All right, so we could do what we did before. Let's say I randomly pick two different elements in my domain. So let's say x1 and x2 are elements in the domain. Okay. If f of x1 equals to f of x2, then that means x1 plus 1 equals x2 plus 1. So we want to show that if f of x1 equals to f of x2, x1 has to equal x2. Okay, that the only way that we can have two y values being equal is if the x values are the same. Okay, so I'm going to set them equal to each other, and let's solve for the x's. So I'm getting rid of the ones, minus 1 on both sides. What do I see? That x1 has to equal to x2. So when the y values are the same, the x values have to be the same. That means the function is one-to-one. Okay, so yes, f of x equals x plus 1 is one-to-one. Okay. All right, so that's what it means to be a one-to-one function. Let's now discuss onto functions. Okay, any questions about one-to-one functions before we move on? Okay, so now a definition for what it means for a function to be onto. So a function f from a to b is called onto or it's also called a surjection. If and only if, by the way, IFF is short for if and only if. Okay. If and only if, for every element B in the codomain B, there is an element A in the domain A with f of A equals B. Okay. So in other words, a function is onto if every element in the codomain is an image. Every element in the codomain has a pre-image. Or in other words, it's onto if the codomain and the range are the same set. Okay? Yes, exactly as you put it. All right, so in other words, this is also the same thing as saying that the range equals the domain, the codomain, as somebody put it. Or another way of saying this is that every element in B has a pre-image. It is the image of something. Okay, so let's give some examples first with Venn diagrams, and then we'll see some examples with some actual functions. Okay. Okay. Here's an example of a function with a Venn diagram. A1 is assigned B1, A2, B2. B3 is an element in my codomain, but it's not in the range, right? B3 has no pre-image. So therefore, this function is not onto. It's not onto because B3 is an element of the codomain, but it's not an image. Okay. Let's see an example of a function that is onto. All right, this is an example of a function here that is onto, right? A1 and A2 are both assigned B1. A3 is assigned B2. So everything in the codomain in set B is an image. It has a pre-image, okay? So this is onto because every element in B, the codomain, has a pre-image. Okay? It is not, however, one-to-one. This is a function. It's not a one-to-one function. Okay? So this is a function. It's onto, but it's not one-to-one. Okay? It is not one-to-one. Okay? Right, exactly, because two inputs give the same output. Okay? Why is it not one-to-one? Again, two inputs give the same output. Right? F of A1 will equal to F of A2. Okay. All right, so we could have functions that are onto but not one-to-one, functions that are one-to-one but not onto, functions that are both, and functions that are neither. Okay. Let's see another example here. So let's say now I give you the function f of x equals x squared. And let's say f is a function from the set of real numbers to the set of real numbers. Is this function onto? What do you guys say? Is this function onto or not? We have one no. What does everybody else say? Any other takers? Does everyone agree? Oh, we have an explanation too. Very nice. Okay. Does everyone agree with Yasir or any disagreements? No one else is brave enough to suggest a possible answer. Okay. Let's see if this function is onto. All right. So to be onto, oh, is the function onto? All right, so let's go over this. Okay. Is this function onto? To be onto, every element in the codomain has to have a pre-image. Okay. So my question is this: are there numbers in the codomain? The codomain here is the set of real numbers. Are there numbers in the codomain that my function cannot be equal to? That my function can never equal to? Okay. And if so, what are they? So Yasser already answered that. The negative numbers, right? X squared can never be negative, all right? So for example, -1 is an element in the codomain, element of the codomain, all right? But my function, f of x equals x squared, can never equal to -1, right? X squared can't equal -1, all right? X squared is always non-negative, right? Domain is a set of real numbers, okay? So my function can never equal to -1. That means -1 has no image. There's no x value that I can plug in from the domain to get -1. So therefore, this function is not onto, okay? It doesn't cover every element in the codomain. So therefore, f of x equals x squared is not onto, okay? Okay. Let's see another example. Let's go back to the other example from before. Let's say I give you the function f of x equals x plus 1, where f is a function from the set of real numbers to the set of real numbers again. Is this function onto? Yes, yeah, that's correct. This one is onto. Okay. Take any real number, any number from the codomain. What element do I have to plug in from my domain to get that number? Just plug in the number that's one less, right? So let's write it this way. So this function is onto, right? Because for every integer y, let's call it y. Remember, y is the same thing as f of x. Okay? For every integer y, there is an integer x such that f of x will equal to y. Okay. What an integer is that? That integer is y minus 1, right? Namely, x equals y minus 1. Okay. So if I want to get y be any, not integer, real number. For every, I meant real number. For every real number, real number y, there is a real number x. There we go. There is a real number x such that f of x equals y, namely x equals y minus 1. Okay. Okay. All right, so that's onto. Somebody's asking if they can say it the other way around. Depends how you word it. I'm not sure exactly what you mean. Really depends on how you word it. All right. Okay. Okay. All right. So let me now move on to the next definition. Okay, this definition is for a function that is a bijection. Okay, so the function f is a bijection. All right, also known as a one-to-one correspondence. If it is both one-to-one and onto. Okay, so any function that is both one-to-one and onto is called a bijection. Okay. All right, so let's see an example here. Let's say we have a function, f of x equals x squared plus 4 over x squared plus 5, where f is a function from the set of real numbers to the set of real numbers. Is this function a bijection? Okay. Well, to be a bijection, it's got to be both one-to-one and onto. Okay. Is this function one-to-one? What do you guys say? Is it one-to-one? It's not going to be 1-to-1, right? Why not? Again, if I plug in -1, I'll get the same thing as if I plug in 1, right? -1 squared plus 4 over -1 squared plus 5. That's going to be the same thing as if I plug in +1, right? Or you could do -2 and 2, -3 and 3, okay? So it's not 1-to-1, right? As soon as I see it's not 1-to-1, I know automatically it's not a bijection, right? Not a bijection. Okay. I don't even have to check to see if it's onto. And by the way, it's not onto either. All right, right. For example, this function can never equal to 0, but 0 is in the codomain. Okay, so this function here is not a bijection. Okay, let's see one more example of this. Let's say I give you a function f from z times z to z. Okay. So we had discussed this a little bit at the beginning of class. All right, this means that I'm plugging into my function the Cartesian product of the set of integers with the set of integers. So I'm plugging in pairs of numbers, okay, and I'm getting out a single integer. All right. Okay, let's say my function f of m comma n is equal to m plus n. Is f onto? Okay, so here I'm plugging in two numbers and I'm getting out a single number, two integers and getting out an integer. So for example, let's say I plugged in f of 3 comma 2, that's equal to 3 plus 2, which is 5. Okay, so you plug in two integers, you get out one integer. Right? If I plug in 1 comma 4, I get 1 plus 4, which is 5. So I automatically see right away that this function is not 1-to-1, right? But that wasn't the question, right? It's not 1-to-1. Why not? Because I can plug in two different values for my input, 3 comma 2 and 1 comma 4, and get the same output. So it's not 1-to-1. But again, that wasn't the question. The question is this function onto, right? And the answer would be yes, right? Because I can get all the integers, I can get every element in my codomain. Just let's say let m be 0 and let n be whatever integer you want, right? So it is onto. Okay. All right. If I let m, let's say, be 0, and then let n be whatever integer you want, you can get all the integers, right? N be 0, -1, 1, -2, 2, -3, 3, and so on and so forth. So you could get all the integers that way. Okay. All right. The sum would just be that integer. Okay. All right. Let's now discuss inverse functions and compositions of functions. Okay, so definition. Let f be a bijection from A to B, okay, from the set A to the set B. The inverse function of f is the function that assigns to an element B belonging to B the unique element A in A such that f of A equals B. The inverse function of f is denoted by f to the -1. Okay, So in other words, if we know that f of a equals b, then the inverse function does the reverse. So f inverse of b equals a. All right. Oh, thank you. The inverse function of f. Thank you very much. The inverse function of f. There should be an f there. Oh, great. Thank you. Thank you for pointing that out. Okay. Okay. So if we had our Venn diagrams here, if f assigns b to a, f inverse does the opposite. Okay. Yeah, I'm going to go back 1 second. Let me scroll back here. Oh, sorry. Okay. All right. So for example, let's say I have some function f, and I know f of 8 equals -2. Then if it has an inverse function, then f inverse of -2 will equal 8. Right? Okay. Now let me give you the definition for the composition of two functions. Let g be a function from a to b. Let f be a function from b to some set c. Okay. The composition of f and g denoted by f with a little circle with followed by g is defined by the following: f of g of x equals this, f of g of x. Okay, so for example, let's say f and g are both functions from the set of real numbers to the set of real numbers. Let's say f of x equals x squared, and g of x equals x plus 2. Okay. F of g of x, their composition. Oh, let me keep the definition in view there for a minute. Okay. So the composition of these two functions in this example is going to be equal to f of g of x. G of x is x plus 2. So what this means is I'm taking g of x and I'm plugging it into the function f. So I get f of x plus 2. Okay. So in f, wherever I have an x, I'm replacing it with x plus 2. So f of g of x becomes x plus 2 squared. Okay. If I square that, I get x plus 2 times x plus 2, which is x squared plus 4x plus 4. What about if I do the reverse? Let's say I do the composition of g and f. So g of f of x. Okay. This is going to give me a different function. All right, this is going to be g of f of x. F of x is x squared. So I get g of x squared. So in the function g of x, wherever I have an x, I replace it with x squared. So that becomes x squared plus 2. Okay. So in general, composition of two functions is not commutative. So f of g will not equal to g of f. Okay. F of g does not equal to g of f. Generally speaking, that will give me two different functions. Okay. The only time that f of g will always equal to g of f is if the two functions are inverses of each other. Okay. So f of f inverse of x will always just be x, and f inverse of f will just be x. Okay. So that's the only exception. But in general, composition of two functions is not invertible. Oh, excuse me, it's not commutative. Okay. All right, any questions on that? All right. So let's finish off this chapter by discussing the floor and ceiling functions, which are two special functions that are used sometimes in discrete math and sometimes in computer science. Okay. Yeah, we're going to finish 2.3 now, section 2.3. Not all of chapter 2. I meant the section, my apologies. Okay. All right, my apologies, I didn't mean to scare you. All right. Okay. So the first is the definition for the floor function. The floor function assigns to the real number x the largest integer that is less than or equal to x. Somebody had a question about inverse functions. Let me define this and then I'll go back and explain that again. Okay. And so the floor function assigns to the real number x the largest integer that is less than or equal to x. Okay. And it's denoted by this symbol here, like that. Okay. The ceiling function assigns to the real number x the smallest integer that is greater than or equal to x. Okay, and it's denoted by this symbol here. Okay, so what kind of brackets are those? All right, they sort of look like square brackets, but for the floor function, there's only a part on the bottom, right? The top part is missing. For the ceiling function, the brackets have the ceiling, but not the floor. Okay, so the floor function only has the floor, the ceiling function only has the ceiling. Okay, so if I asked you to evaluate this number, okay, This is the floor function, and I'm plugging in 1/2 into the floor function. So for the floor function, I'm looking for the greatest integer that is less than or equal to the given number. So what is the greatest integer less than or equal to 1/2? What would this be equal to? Okay, yeah, that would be equal to 0. Right, this is equal to 0. So in other words, with the floor function, we're always rounding down to the closest integer. Okay, if I plugged in 3.7 into this thing, I would get 3. If I plugged in 2.9, I would get 2. Okay, so we're always rounding down. If I plug in, let's say 4 into this thing, I would get 4, right? Because it's less than or equal to. So if it's an integer, it stays the same. Okay. What about for the following? Let's say I plug in negative 1/2 into the floor function. What will that be equal to? Yep, -1. Okay, so remember we're rounding down. It's -1, not 0. All right. What about the ceiling function? The ceiling function does the reverse. So for the ceiling function, we're rounding up to the closest integer. So if I plug in 1/2 into the ceiling function, I get 1. If I plug in 3.7, I get 4. If I plug in 2.9, I get 3. If I plug in 4, I get 4. If I plug in -1/2, I get 0. So it's rounding up to the closest integer. Okay. Another function that we could discuss is the factorial function. Right. Right, I'm sure most of you are familiar with factorials. The factorial function is a function f from the set of natural numbers to z plus, okay? And it's defined as follows. F of n equals to n factorial, right? What does n factorial mean? N factorial is equal to n times n minus 1 times n minus 2 all the way down to 1, right? So in other words, it's the product of all the positive integers less than or equal to n. All right. So for example, 4 factorial would be 4 times 3 times 2 times 1. Okay. 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay. Just by definition, 0 factorial is equal to 1. Okay. 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 Also, is the floor and ceiling functions, are they one-to-one? Let's say from the floor and ceiling functions, let's say they're from the set of real numbers to the set of real numbers. Are those functions one-to-one? Not one-to-one. Okay. What does everybody else say? Are the floor and ceiling functions one-to-one? Does everyone agree they're not one-to-one? Anyone disagree? Yeah. Right. So those functions are not one-to-one. Yeah, I'm asking about the previous functions. The floor and ceiling functions, okay? Are they one-to-one? The answer is no. And I can demonstrate that by way of example, right? If I plug in 1.6 into the floor function, I get 1. If I plug in 1.7, I get 1. So I have different inputs giving me the same output. It's not one-to-one. Okay, and it's the same for the ceiling function. We have a different question. Why does 0 factorial equal to 1? It's just defined as that. All right. So 0 factorial is just defined as being equal to 1. You're right. There is no negatives, right? And you can only plug in, let me go back to the factorial function here for a moment. The domain is the set of natural numbers. So you're not allowed to plug in anything negative, only non-negative numbers. Okay. All right. I think we also had a question before about inverse functions. Did somebody want me to go back and explain something? Yes. Okay. What was your question about inverse functions, if you don't mind me asking? Okay. Was it just the last thing I said about inverse functions? Was that your question? Okay. So basically, the last thing I said about was that the thing with the composition of a function and its inverse? I said the last thing I said was basically that if you take a composition of a function f with its inverse, they're basically going to cancel each other out, and you'll just be left with x. Okay, and it doesn't matter the order. There, the order doesn't matter. So a composition of f and f inverse, or you do the reverse f inverse of f, they'll both equal x. Okay, either way they'll cancel each other out. Okay, so that's what I was saying. F of f inverse of x will equal to f inverse of x will equal to x. Okay, so that's the only time really that a function, the composition will be the same either way. Okay. All right. So we're going to stop here for today. Okay. So the quiz, due to technical difficulties, has been postponed to Monday. It will still only be on 2.1 and 2.2. I do not plan to change that. Okay. If I'm still running into issues with Blackboard, I'll let everybody know through email. Okay, and once I figure out my issues with Blackboard, I'll have all your grades up. And again, if I can't get them up, I'll just email those to you as well. Okay. On Google Forms, that could be an option. Let me see if I can get Blackboard to work, and if not, we'll try something else. Okay. All right, everyone, let's do the attendance, and I will see everybody next time. Okay. All right, everyone, I'm going to head out.